This is a video for AQA Further Pure Mathematics, Sequences and Series, Section 4.4, L'Hopital's Rule. We saw in a previous video how if a function was indeterminate at x equal to 0, we could use Maclaurin's theories to try and express it in a different way so we could evaluate a limit as x approaches 0. Here's a slightly different situation where this time we've got a function which is indeterminate at x equal to 1. So we can see that when x equal to 1 here, we've got log 1 over 1 minus 1, and both of those are 0. So we can see that log 1 divided by 1 squared minus 1 is 0 over 0. So we can't actually determine the value when x equal to 1. So what we want to be able to express is the limit as x approaches 1 of that function to see if that can be evaluated. Now this is one of a family of limits that we can use L'Hopital's rule to find. The rule can be used to find limits of the form f of x over g of x, so we've got a function on the top line and the bottom line, where either f of x and g of x approach 0 as x approaches c, or f of x and g of x both approach infinity as x approaches c. And where I said infinity, that could of course be plus or minus infinity. So L'Hopital's rule says that the limit as x approaches c of f of x over g of x is actually equal to the limit of the derivatives f of dashed x divided by g dashed x. So if we look at the particular function that we were considering a minute ago, then we can say that this limit of log x over x squared minus 1 as x approaches 1 must be the same as the limit of their derivatives. So the derivative of log x is 1 over x, and the derivative of x squared minus 1 is 2x. So we have 1 over x divided by 2x, and therefore that's equal to 1 over 2, and that's the limit as x is approaching 1, and therefore we have that that is equal to a half. Now we just need to check, make sure that we can actually apply L'Hopital's rule. We should have done this previously perhaps, and we can see that log of 1 and x squared minus 1, so 1 squared minus 1 is equal to 0 over 0. So we're okay, they both are approaching 0 or equal to 0. Well, a couple of more examples. The first one, e to the 2x minus 1 over x as x approaches 0. Now obviously we could do this using Maclaurin series, however it's going to be easier probably to do this by using L'Hopital's rule, so we can differentiate, and that should be much quicker in general. So for the first one, we first of all need to check then that e to the 0 minus 1 is definitely equal to 0, which it is, and obviously when x is equal to 0, then that means that we have 0 on top and bottom line. So both the functions approach 0, so we can say using L'Hopital's rule that this must be equal to the limit as x approaches 0, and then taking the derivatives, well the derivative of e to the 2x is e to the 2x multiplied by 2, and then the derivative of x is 1. As x approaches 0 then, the top line is 2 and the bottom line 1, so the limit is equal to 2. For the second one, as x approaches infinity, both e to the 2x minus 1 approaches infinity, and obviously x approaches infinity. So yes, this is an, if you like, an infinity over infinity case. where both the functions are approaching infinity as x approaches infinity. Therefore, we can say that the limit as x approaches infinity must be equal to the limit of the derivatives 2e to the 2x divided by 1 as x approaches infinity. So we can see therefore that this is also approaching infinity. In the second example then, again just checking that both the numerator and the denominator, this time as x approaches infinity, both of those approach infinity. So we know that log x plus 3 approaches infinity and x plus 4 also tends to infinity, so that we can use L'Hopital's rule and say that the limit of the functions must be equal to the limit as x approaches infinity of their derivatives. So on the top we've got 1 over x, and the bottom we've got 1. And therefore we can say that the limit is equal to the limit of 1 over x as x approaches infinity, and that's equal to 0. As a final example, look at x squared 1 over 1 minus cos x as x approaches 0. Of course we know that 0 squared is equal to 0 and 1 minus cos 0 is equal to 0, so yes, we can use L'Hopital's rule. Therefore we can say that the limit as x approaches 0 of x squared over 1 minus cos x is the limit as x approaches 0 of the derivatives, which is 2x, and then on the bottom line we have got sine x. The derivative of negative cos x is sine x. Now if we look here, we can see that if we put 0 into the numerator, then we get 0, and also into the denominator. So we've still got something which we can't actually evaluate correctly. But we can apply L'Hopital's rule again, because we've got a situation where we've got two functions again, both equal to 0 when x equals 0. We can differentiate again and say that this must be the limit of x approaches 0 of 2 divided by the derivative of sine x, which is cos x. But as x approaches 0, we can say that cos x is close to 1, and therefore we've got this being equal to 2. And just to confirm that, here we have a graph showing the function x squared over 1 minus cos x, and you can see that when x is equal to 0, we've got the value of y equal to 2, which is what we found from our limit. That's the end of this video on L'Hopital's rule, and indeed it's the end of the series of videos, Sequences and Series, Section 4.